Hi folks, we're starting a new 2-week module on climate change, which you may notice a few years ago was called global warming, and that sort of phrase has sort of fallen out of favor, and that's because the term global warming doesn't really represent the depth and breadth of climate shift, which we'll be talking about here. In this particular PowerPoint, we're just talking about natural changes in climate. Changes in climate that have nothing to do with people, and changes in climate that have been going on since the beginning of the Earth 4.6 billion years ago. One of the things that can impact the likelihood of there being ice ages on Earth has to do with plate tectonics, and specifically that has to do with the location of the continents around the Earth. Currently, about 70% of land masses on Earth are in the northern hemisphere. This actually makes it more likely that on Earth we will experience an ice age, and that's because what you need really to generate an ice age on Earth is a series of cool summers. Now, why cool summers? Because you need to have more snow fall in the winter than can melt in the summer. So if you have a series of cool summers year after year after year, you can see how you can build up more and more snow and ice annually. So because we have so much landmass in the northern hemisphere, we are in a position where these cold summers could, over time, drive the Earth into an ice age. And we'll talk a little bit more about that maybe next week. But the Earth, we know, hasn't always had land masses distributed in this way. If we had a more even distribution of land between the northern and southern hemispheres, or if we had a lot of land around the tropics in the equator, in the equatorial regions, again, that propensity would be lower. And in the last 2 million years, Earth has experienced several ice ages, largely because of this continental configuration. Another long-term trend that can impact climate on Earth is volcanic activity. Now, when we learned about supervolcanoes, we learned about short-term cooling that was the result of volcanic activity, but actually in the long term, volcanoes cause the Earth to warm, and that's because of the gases that are emitted during volcanic eruptions, largely water vapor and carbon dioxide, which are both of what are called greenhouse gases. Greenhouse gases are gases in the atmosphere that basically trap heat around the Earth. If you want to think about it as like a blanket that basically you put on at night to trap your own body heat, the higher the concentration of greenhouse gases, the more heat gets trapped. So it's like the more blankets that you're putting on at night. And while it's good to have some greenhouse gases in the atmosphere because they help to sort of regulate Earth's climate so we don't have huge shifts in temperature on a daily basis, the more greenhouse gases you have, the higher the concentration so the higher the amount of heat gets trapped in Earth's lower atmosphere. So even though volcanoes generally are a short-term cooling impact on climate, like maybe 10 to 50 years, for instance, if you're having a really big volcanic eruption, for long-term trends, they actually cause warming. It'll react chemically with the rock and will basically turn the rock, break it down, and turn it into clay particles. So what's happening here is first the carbon dioxide gets trapped in the carbonic acid and then gets trapped in clay particles. And then the clay particles will settle to Earth, and basically what this is doing is taking carbon dioxide out of the atmosphere and storing it on Earth in the form of clay particles. Now, clay is just like mud. It's really fine-grained sediment that is probably the most common type of sediment on Earth. Another long-term cooling trend is the creation of fossil fuels. There are 3 big types of fossil fuels that we use in industrialized countries, and that would be petroleum and natural gas and coal. They're called fossil fuels because they're literally made of the remains of dead organisms, fossils basically. Everything alive on Earth is composed of carbon, and when those organisms die, whether it's in the ocean or on land, for the most part things get decomposed by bacteria and other creepy creatures. But if they don't get decomposed, what can happen is that they can settle to the bottom of an ocean or another landmass, And if they're rapidly buried to the point where they don't get decomposed, the carbon that they are composed of over really long periods of time, like hundreds of millions of years, that carbon and the hydrogen in those dead animals will kind of recrystallize, and there's a series of chemical reactions that will occur that will basically turn that carbon into hydrocarbons, like coal and gas and oil. And then what we can do as humans is we can find those deposits, pump them out, put them into our car, and when we drive our car, we're breaking those hydrocarbon bonds from those dead plants and animals. We're literally taking the carbon from those dead animals that was stored below ground, and we're burning it and sort of reintroducing it to the atmosphere. And so we're, again, burning the organic remains of these organisms. Now, because the organisms are made of carbon, when they get buried, it's removing carbon from the ocean atmosphere system. So removing carbon dioxide means less greenhouse gases, means generally cooler temperatures. And this is why fossil fuels are non-renewable. Look at the time frame on this diagram. 300 to 400 million years to make an oil and gas deposit. It's just not something that's renewable in any sort of a reasonable time frame. This graph is kind of interesting, and I'm going to kind of walk you through it. If you look at the bottom right, you see 0 at the bottom. That represents today. And as you go from the 0 line on the x-axis and you head to the left, you see that we're going back in time, 50 million years, 200 million years, all the way to 400 million years. And on the y-axis here, you have the concentration of carbon dioxide in the atmosphere. The areas that are striped red are time periods on Earth that are believed to be warmer than they are today. The blue areas are times on Earth when it's believed that Earth was colder or as cold as it is today. And then the black area, sort of the zigzaggy part in the center, represents estimations of carbon dioxide content over time. The top of the black part represents the upper estimate, the bottom of the black part is the lower estimate. And what you can see is that there are times when basically scientists have a pretty good idea of what carbon dioxide levels were in the atmosphere, and then there's other times when they really are just kind of making a stab in the dark. So there's a few cool things that we can see in this diagram. The first thing is that in general it's actually common for Earth to be warmer than it is today, right? There's a lot of red on this diagram. There's not too many times in Earth history when it's been as cold or colder than it is today. If you look probably for the last 30 million years or so, scientists have a pretty good handle on what carbon dioxide was then, but during the times of the dinosaurs, which roughly are from 250-ish million years to about 60 million years ago, you see that they're kind of all over the place, even though it's generally believed that it was warmer than it is today. So that's interesting. How scientists get this carbon dioxide curve is through a bunch of different methods. When we look closer to 0, closer to today, those come from lake sediments, from ice core, from ocean core, and as we get further back, the way scientists estimate carbon dioxide levels has to do with the chemistry of different rocks and the organisms that we find in rock layers, so fossils and the chemistry of the rocks. So anyway, this is just kind of an interesting diagram because it shows you, even though there's so much talk about climate change today, that climate change has gone on well before the Industrial Revolution in the 1850s. There are also what geologists consider shorter-term climate cycles, and these climate cycles vary probably on 100,000-year cycles and less. Probably the number one short-term impact on climate involves changes in Earth's orbit around the Sun. And one of those changes is eccentricity. The eccentricity of Earth's orbit is the shift from a more circular orbit to a more elliptical orbit. There are 3 different orbital parameters we're going to talk about. Each one influences Earth's climate. Not one of them actually controls Earth's climate, however. If you look at this diagram of eccentricity, you'll see that Earth's orbit around the Sun, which takes about a year, varies from a more circular orbit to a more elliptical orbit over time. And it varies on about 100,000-year cycle. So this is even though it's a short-term cycle, 100,000 years seems pretty long. And when you look, what do you think? Do you think the Earth is more likely to experience an ice age when it has a more circular orbit or a more elliptical orbit? Well, hopefully you think it's an elliptical orbit, because that's the way it is. And that is because physically Earth is just farther away from the sun, and so it's receiving less direct rays of the sun's radiation. So again, this is just a natural shift that happens in Earth's orbit about every 100,000 years and has an influence in how much heat Earth is going to be able to absorb. Another impact on Earth's climate has to do with the tilt of the Earth, or the obliquity. So if you've ever bought a globe, you know that globes are always offset at about 23.5 degrees, and that's because that is the tilt of the Earth as it orbits the sun. That tilt, or that obliquity, is not constant though, and on about a 40,000 year time scale or so, it'll vary from about 22 degrees, which is the minimum tilt, to about 24.5 degrees. This doesn't seem like a huge difference, right? But the deal is, when the Earth is at a maximum tilt, the poles are receiving a little bit less solar radiation than they would be if it was at a more vertical orientation. So basically what that means is when obliquity is at like a maximum, then Earth's poles are likely to get progressively less solar radiation and then therefore be more inclined to be in an ice age. Now remember, each one of these only has an influence, not one is a controlling factor. The final and maybe the most confusing orbital force is called Earth's precession. And this diagram is weird. The red thing on the right is supposed to represent like a kid's toy that's like a top, where you pump the top and it spins around and it wobbles back and forth. And the Earth's wobble, or its precession, basically means that while in this case Earth is oriented kind of to the northwest, pointing towards the North Star, so when we look up at night we can see the North Star as it orbits around the sun. Sometimes Earth isn't oriented towards the sun, towards the North Star at all, and Earth's wobble will rotate so that we can't see the North Star at night, and it can instead see a different star called Vega. And what this basically boils down to is that as Earth moves around the sun, currently we're in the northern hemisphere, we're closer to the sun during our winter, and we're farther away from the sun during our summer as Earth travels around the globe. However, the Earth isn't always oriented in that same exact direction. If Earth were oriented so that we were facing Vega, the star Vega, then we would actually be closer to the sun during our summer and farther from the sun during our winter. And remember we said that you need cold summers to make an ice age. So that means that we're currently, if precession was the only thing that mattered on Earth, Earth might be in an ice age, because again we're farther from the sun currently during our summers. So we should be having colder summers now than we would have if we were oriented differently. So again, this controls our physical distance from the sun at different times in the year. Get ready, because the next diagram is really ugly. I'm going to walk you through this. It's going to get uglier. Every time you click the mouse, it's going to get a little uglier. What you have on the top three lines of this, three squiggles in this diagram, are those three orbital changes that we just talked about. So precession, again, is that wobble of the Earth. And if you go to the left-hand side of the graph, you'll see today, and it goes back about 1 million years over time, and that red squiggle represents how the Earth's wobble has changed over the last 1 million years, and it's changed on about a 24,000 year time scale. The next line down, the green line, is obliquity. That's the tilt of the Earth, and it has also varied in the last 1 million years, and it varies on about a 40,000 year cycle. Astronomers, by the way, calculate these sorts of orbital changes. And then the third blue line down is the eccentricity. That's the change in Earth's orbit as it orbits the sun from a more circular orbit to a more elliptical orbit, and it varies on about a 100,000 year cycle. We're going to skip the solar forcing squiggle for now and go all the way down to stages of glaciation. The way these temperatures basically get estimated is by using ice core, and you'll do an assignment called Warnings from the Ice where you'll learn how these ice core are collected and analyzed. But what you have to know here is that the high peaks in this squiggle, which are also marked with little gray vertical lines, those represent warm periods over the last million years. And you might notice that the warm periods are a heck of a lot shorter than the cold periods, which are the parts that are white in this squiggle. So warm periods are really brief relative to ice ages. If you click the mouse, a whole bunch of delightful vertical lines will show up, and those correspond to the warming periods. As you look up and see those three orbital parameters again, orbital variations, your precession, your obliquity, and your eccentricity, look and see which one you think most closely corresponds to those warming periods. What'd you see? If you notice that the eccentricity curve, every time there's sort of a peak in eccentricity, meaning closer to circular, every time there's a peak in the eccentricity, there tends to be a warming period. So what this graph is telling us is that when we look at these three parameters, eccentricity turns out to be, in terms of short-term climate shift, the most significant control of climate on Earth.